as always, the chemistry tutor here, and I'll be explaining the concept of gas laws and all you need to know as regards gas laws. Okay, so I want you to pay maximum attention. So everything I'm going to be discussing, by the time I'm done with this video, you should be good. I mean, you should be good with gas laws and you don't have problem as regards it. Okay, now the first thing you have to understand is that what is actually a gas. Yeah, good evening, how are you? What is actually a gas, right? What's actually a gas? That's the first question. You would agree with me that gas is a state of matter. It's one of the state of matter, right? Yeah, good evening, Debbie. Gas is one of the states of matter, right? You would agree with me. So just like every other thing is a state of matter, what are the other ones? We have solid, we have liquid, but there's something very peculiar about gases, right? Please like this live so that other people can join. Like this live so that other people can join, please, so I would know. Yeah, good evening, Debbie. Good evening, Ezekiel. Welcome. So I want to teach you gas laws, and you don't have to worry about it again now. But that means if you're talking about the law that binds gases, we must first understand what this is all about. Thank you so much. Thank you for that. Thank you, I appreciate. Thank you. Now that means we'll first understand what gases are all about. So the first thing is gas is a state, right, of matter with weak intermolecular forces. Now, why is this thing important? It is important because we know how gas tends to move, because they move what? They move freely. So because gases move freely, that means the force that binds gases, that binds the molecule of gases, it means that kind of force is actually weak. So that is what even brings about them moving freely, right? Because it is important that you know this. It is important that you know this. Now, you have to also understand the fact that gases, as you're seeing them, they can move in containers, or they can tend to move even though and tends to beat or eat up the container. Let's say they are moving like this, they are moving like this, they are moving like this. Can you see the way they are moving? They can move and even be eating up this container. So they have weak intermolecular forces. Another thing I used to explain this with is that you should also understand that if you tie someone, for instance, to a pillar, let's say you tie someone to a pillar, right? If you tie this person to a pillar, things happen. The only way you can know how strong this person is to this pillar is the force that used to bind it. If the forces that used to bind this guy to this pillar is weak, what do you expect? You expect that in due time this person should be able to run away, right? So that is what happened. So it's because of the forces that tends to bind gases together, the molecules of gases, the forces that tends to bind them together is weak. That's why they can tend to move freely, unlike solid that vibrates at a fixed point. Good evening, Dr. Yeah, RV, thank you so much, I appreciate. Hi, yes, Fetia, thank you. Welcome. If you are here, please share this live to other people so that they can learn. Now, but before we go, that means there's something we call 5 assumptions of an ideal gas. Please note, there's not like an ideal gas. if anything you want to know today is that ideal gas do not exist. Ideal gases do not exist. We only have real gases. Ideal gases do not exist. We only have real gases. Now that means you have to understand that there's something. If they don't exist, then what are the assumptions? Right? That is what you have to understand by these 5 theories or 5 assumptions of kinetic theory. Now, if you understand these things, you are good to go. What is the first one? The first one states that gases move in a, please don't cram this thing, in a constant motion. That's the first thing. Gases move in a constant motion. How do I know? I'll be using, thank you for liking, I'll be using a very important thing to explain this. Now, what am I going to use? I'm going to be using when you are boiling vapor, when you are boiling water and you are heating the water up, the liquid that you have here will translate into vapor, right? And this vapor can tend to be moving like this. They will be moving tangentially. Can you see the way these are the vapor? Can you see the way they are moving tangentially, right? Now, this movement of this tangentially is constant, and in fact they used to use the word linear, right? Well done, Bishop, well done. Can you guys hear me? Hope you guys can hear me. So this movement is constant. In fact, they say linear or straight. So don't cram, please. Linear or straight. Don't forget, I said there's no ideal gas. We only have what? Real gases. We only have real gases. Never forget, these are the gases that we have. So what we are just doing that we talk about here is the assumptions of an ideal gas. Now, that's number 1. Number 2, this is the first one, that gases move in a constant linear or straight motion. Now, what's number 2? Is that gases collide, right? Definitely. And after such collision, don't cram this thing, after such collision, they tend to move in a what? In a perfectly elastic manner. That's the second one. You don't cram it. It's simple. I mean, you cannot be in a container and be boiling and not collide. But look at the word elastic, and they move like an elastic ball. Now, what does it mean? Look at it. If you move like an elastic, let's say you have a wall. Yeah, you have a wall. The moment you throw an elastic ball, yeah, what do you expect something that is elastic to do? It will bounce back. That's what it means. Once you throw it here, it will bounce back. But don't forget, this is an assumption of an ideal. Normally, a normal gas, a real gas, will not do that. A real gas will move, will be perfectly inelastic. A real gas will. But these are the assumptions that we have an ideal gas. Are you with me? Are you with me? I want to be sure. This is a word that I just used to explain. When you hit the ball, elastic, look at it. Are you with me? I want to be sure you are with me. Can you comment yes, that you are with me? Yes, just comment yes. Okay, Fitia is with me. Yes, good. Right? Good, fantastic. Everything is with me. So that's number 3. That's number 2. Now, what is number 3 assumption? Is that the volume, look at, don't cram, the volume of the gas, by the time you compared to the volume of the container, it is said to be negligible. Now, when we say something is negligible, what do you mean? Negligible is easy, that you almost tend to not rate it at all. So when you don't rate someone or you don't rate something, you say it is negligible. Now, what it means is that by the time you compare the gas as it's moving like this, when you compare this gas as it's moving like this, and you now compare it to the volume of this container that it is in, this volume of this guy, it is assumed to be what? To be 0. So, or what we use the word negligible. Do you understand? It's assumed to be 0 or negligible. That's number 3. They are just 5. Number 4 is that the intermolecular forces within gas particles, see, don't cram this thing on, is negligible. So look at it, the forces are negligible, the volume are negligible. When they collide, they move in a perfectly elastic manner. That is, they collide and bounce back, just like I said. When they collide, they bounce back. That's what they mean by perfectly elastic. Then aside from that, they also move in a constant linear motion. Now the 5th one, this one is very, very important because you need it, right? This 5th one is very, very important. It states that the kinetic energy of gas molecules is directly proportional. Kinetic energy of gas molecule is directly proportional to the temperature. In fact, this is what brings about the new definition of temperature, and I will tell you. Please, if you have not snapped it, take a picture now. Right? The kinetic energy of gases is directly proportional to the temperature, and I will explain. Imagine this is a container of water. Right? This is a container of water. Imagine you are eating this container. If you want this water to boil faster, what will you do? Oyindamala, what will you do if you want to boil water very fast? What will you do? What will you do if you want to boil the water very fast? What will you do? What will you do? Debbie, what will you do? If you want to boil this container, don't forget, these are molecules inside, right? If you want it to boil faster, this is it. So what will you do? It's easy. You increase the temperature. Thank you, Fetia. You increase the temperature, right? So by you increasing the temperature here, that means the molecules will move faster. And what are you increasing? Kinetic energy. So that's why the kinetic energy is directly proportional to temperature, which is the 5th assumption. Demon, do you get that now? I mean, if you want to boil water at home, what do? You tend to increase the temperature so that it will boil faster. So that is it, because you want to increase the motion, the random motion that these guys are taking. So you want to increase. So these are the 5 assumptions of an ideal gas. These are the 5 assumptions of an ideal gas. Never forget this. It must always work with you, and it's easy. It's easy. Never forget, it must always work with you. Okay? These are the 5 assumptions of an ideal gas. Just like I said, there's nothing like ideal gas. There's no, just like when we talk about what's it called? When we talk about machine, there's no machine that has an efficiency of what? Of 100%. No, it doesn't take place every day. It doesn't take place every day. I just decided to come today. But follow me anyways. If it comes, you will know. So no machine is ideal. Just like motor. In fact, I think I read somewhere that the highest efficiency of motor, a car, is 45%. So which means, yes, you're welcome, Code Rise. You can also join my WhatsApp class if you want to. You can join it. So now, the highest percentage of a car is set to 45%. So that means no, it's not. No machine is 100%, except an ideal machine. Exactly, because that's what ideal is already there. You understand? But the question is there actually an ideal machine? Is there a machine known as ideal machine? You understand? One or two things would have been lost in one way or the other. But because of friction, because of different things. So if you build a new car and they say that the efficiency is 45%, so you understand what that means. So, but the idea is this: when we talk about gases, there's no ideal gas, but those things were the assumption that we made that, oh, if there's actually going to be an ideal gas, these things will happen, right? So we now want to go further and build the laws. So the laws that we need to actually take note are very important. Now we're talking about Robert Boyle's law. We're talking about Charles' law. We're talking about Avogadro's law. We're talking about Gay-Lussac's. Also, don't forget that another name for Gay-Lussac's law is actually pressure law. Now, don't forget that this Gay-Lussac's law here is not from the Gay-Lussac's law we used to state in proper like Gay-Lussac's law when we talk about, volume combining a fixed whole number ratio. But yeah, we are just, what I want you to know that is the pressure law that I want to talk about here. Then the general gas equation. Then aside from that, right, you also need to know what we call ideal gas equation. Now, this from ideal gas equation, you must understand, number one thing that you must understand is conditions that allow for deviation from ideal behavior. Ideal behavior. This one is a proper JAMB question. I have a video on that. You can follow me, you will see it. I have a video on this. Then conditions for ideal gas. So if by the time you know all this, you are home and dry. So let's, pressure law is different. No, that's how I let you know. These guys, they are the same in physics. That's what I'm trying to let you know, right? But in chemistry, when we talk about Gay-Lussac's law, most of the times you want to state that law that states that, oh, when gases combine, they do so in volume and bear a simple number ratio. That is the Gay-Lussac's law in chemistry. But please note, I'm telling you today, Gay-Lussac's law and pressure law, they are the same in physics. So that's why I have to put this here so that you understand what I'm saying, okay? They are the same. Gay-Lussac's law, pressure law, if they ask you this question in physics, it's the same thing. But in chemistry, because chemistry tends to talk about, don't forget, gas law is both in chemistry and physics. So that is why you have to understand that Gay-Lussac's law is also the same thing as pressure law, right, in physics. But Gay-Lussac's law has its own definite law in chemistry. Okay, so please take note of that. So now let's deal with it one by one. Now, what is this guy says, Boyle's law? What is he trying to say? Yes, combining volume. Gay-Lussac's law of combining volume, exactly. So which state that when gases combine, please note, when gases combine, they do so in volume and bear a simple whole number ratio. But in physics, they are the same thing. It's also the same thing. But that's not what that's not what pressure law states in physics. So there's a pressure law that I'm going to state. But just follow through. Don't worry. I know I've been teaching this thing for 6 years now. It's not place. Now, what is Boyle's law? Now, this guy actually, did something. What did he do? He fixed some factors or some quantity and see what happens to them. That's what he did. So he stated that the pressure of a fixed mass of gas is directly proportional to the volume. That means I said directly, is inversely, that's a mistake. Please correct that. Is inversely is not directly, is inversely proportional to the volume, provided the temperature remains What does it mean? That means there's a mathematical representation. Mathematical representation. Now what does it mean? Pressure is inversely proportional to volume. Now in any time when you are doing this, you must know that if I want to change this proportionality sign to an equal to sign, I must always introduce a proportionality constant K, then over V. Now don't also forget what is constant is the two of them, not only this. So that's why I must cross multiply. Then I'll say PV is equal to constant. Now this is because I'm considering just one thing. So that's why if I'm considering two things, I will not say P1 V1 equals to P2 V2. It can even be equal to P3 V3. Now what does this statement mean? Let me explain to you. Now hope you get what I'm doing. I want to be sure. It means that the higher the pressure, the lower the volume. Now if you have a volume like this that is high, as big as this, right? Now because the volume is 2V, right? Can you see? The volume is 2V because we can have a smaller volume which is just V. So in this case, because the volume is high, you expect that the pressure can be halved, right? Yes, we can have, oh sorry, thank you for that. It can go on and on like that. So because the volume is high, the pressure is halved. Or don't let me just use figures like this, just so that when you have high volume, pressure is what is low. When you have low volume, pressure is high. Now how can I make you understand? Imagine your room right now. Just imagine as you are in your room and I decided to bring 1,000 people in your room alone. Do you think the pressure will be low or high? 1,000 people in your room, do you think the pressure will be low or high? Pressure is, the way they fight inside, the way they disorganize, the way those things are disorganized. So if I bring 1,000 people in your room right now, I need an answer. Do you think the pressure will be low or high? Nobody's answering. You guys are sleeping. Do you think the pressure will be low or high if I bring 1,000 people in your room? I said if I bring 1,000 people into your room right now, do you think the pressure will be low or high? Now it's going to be high definitely because the volume of your room is small. But if I take, you can't hear the question. Can you hear the question now? I said if I bring 1,000 people into your room right now, do you think the pressure will be low or high? And someone answered that it's going to be high. Exactly, it's going to be high because your room is small. But let's imagine I decided to take down 1,000 people to a field, a big field. What happened to the pressure? The pressure will be low because the volume is high. A field is a large volume. Sure, you understand that? So please take note of this. Now, if you understand this, we now want to go to graphical representation. So that is, the graphical representation is very easy to know, but students don't tend to understand graphical representation. Now what do I mean by graphical representation? How do you identify this? Now look at it. I can have P here. Now don't forget, pressure is inversely proportional to volume. Sir, I have some questions I am unable to solve. I don't know if you can help. David from RLT. I don't know. So maybe that, if you, I think there's my number. If you have my number, we can talk, sharp. Now P against, now don't forget, I can state this thing different ways. This P can be linked to this guy, right? Don't worry, just follow through. Now if I put P here and I put V here, the statement states that the higher the pressure, the lower the volume, right? Now let's see. That means, let me just put a number so that you understand. I don't want to use something, I don't want to do abstract things. So the higher the what, the higher the pressure, that means this is a high pressure, the lower the volume. With this is low volume. So what do I need? Because don't forget, I'm plotting P against V. So because the pressure is high, so I will plot it against. So that's why you see something like this. Now you see this one will go and meet this. So you can see the lower the pressure, the higher the volume. So this one will go and meet this. Then you can see this is one, low pressure meeting higher volume. Can you see? So this is the graph that you guys see every day. Can you see that graph? So these are, they call that, oh my god, I didn't pick up this, I'm sorry, I didn't see that. So these are the pick up that your graph that you see when they plot pressure against volume, right? Don't forget, P is inversely proportional to V, right? Do you get that? Now I can also have another graph such that when P is plotted against 1 over V, right? Now if you understand very well, you see that when P is set like this, I can take this thing as one thing, as a O, and say, oh, P is actually directly proportional. Look at my word, P is directly proportional to 1 over V, but P is inversely proportional to V. If I've used the word inversely, I'll pick up this one, then it's only V I will mention. But if I want to use the word directly, I will mention the two of them, because that's what it means. P is directly to 1 over V. I mean, now this guy is directly to the whole of this guy. So that's what it means. So by the time I'm doing that for this, that means I will have a straight line, because it is a direct proportion. As this one increases, 1 over V increases, not V. As P increases, 1 over V increases. Very easy. So that's why I say this guy is going to be a straight line. You don't need to cram. They are very easy stuff. They are very easy things. Okay, so you don't need to cram all these things. I don't like when my student crams. Do you understand? Are we good? So this is the first graph, this is the second graph. Do you get that? Are you good? Are you good? Are you good? Are you good? I want to see your response. So that is that. Yes, sir. Okay. Hey, at your tummy, where don't you get to? Where exactly? Okay, I don't know. Where don't you get? Okay, so that is that. Maybe you can well done, sir. Thank you. Maybe you can later rewatch the video. So the second thing is Charles' law. Now Charles' law is straightforward too. Charles' law just say that the volume, the second graph. Okay, I just explained that the statement is P is inversely proportional to 1 over V. Sorry, P is inversely proportional to V, because I've used the word inversely. But if I want to take this thing as 1, I will say P is directly proportional to 1 over V. So when I'm plotting P against 1 over V, because this thing means directly proportional, it's going to be a straight line graph. That means as P increases, the whole of 1 over V will increase, not V. You understand? So that is what I explained. So volume, is directly proportional to temperature, provided the pressure is constant. Provided the pressure is constant. Okay, so now what do I mean? Volume. Okay, I think I need to write somewhere else. So volume is directly proportional to temperature. Don't forget the rule. If I want to change this sign to an equal to sign, there must be a constant, KT. Also, do not forget that what is constant is not only V, it is the two of them. So I must find a way to eliminate T beside it. So you divide both sides by T. So this one will cancel this. Then that means that constant, that V over T is now what is equal to a constant. So if I now want to think of 2, I will say V1 T1 equals to V2 over T2. So this is Charles' law. Okay, that answers that. Now let's go. The next one is pressure law, or what they, just like I said, what they note as Gay-Lussac's law in physics. So what is pressure law? Pressure law states that what the pressure is directly proportional to what temperature, provided what will be remain constant, provided the volume is constant. So all this K you are seeing here is all these things that we are talking about. So for Charles' law, it will be pressure, that will be K. For Boyle's law, it will be temperature, that will be K. For pressure law, it will be volume, that will be K. So take note of that. So mathematically, P is directly proportional to T. Now don't forget, I want to change this sign to an equal to sign. So it must be K over T. So that's why P divided by T equals to KT divided by T. So this will go with this, so that P over T equals to K. So if I want to think of many, I will say P1 over T1 equals to P2 over T2. So this is pressure law. Right, this is pressure law. Now, I hope we get it up to this stage. Do we get up to this stage? Do we get up to this stage? Do you get it up to this stage? I want to be sure. Good. You guys are smart. So now, if I combine, just note, if I combine Boyle's law, Charles' law, and pressure law, that's when I will have that general equation, which is like, Boyle's law already is P1 V1. Charles' law is what? V1 over T1. Pressure law is what? P1 over T1. So by the time I pick what is on top, what is below, I will have P1 V1, because V1 P1 is everywhere. Then T1 is what is here. So I'm considering 2. It will be P1 V1 equals to P2 V2 over T2. So that is what happens here. So this is the general gas equation. This is general gas equation. Alright, so now let's move. There's one very guy, Avogadro's law. Now, I know that some of you might not go to secondary school, public secondary school, you might go to private school. There's a particular song we used to sing there. Avogadro's law ló sọ wípé equal volume of all gases at the same temperature and pressure contain the same number of molecules. So what do I mean? It's just saying, leave that statement. Just know that the temperature and pressure are constant, first of all. But what it's saying is that the number of molecules is directly proportional to what? To the volume. That is what Avogadro is just saying. So from here, I can say N is direction to V. So if I want to remove this, I will say N equals to KV. The same way, divide both sides by V. Then I will have this, then N over V equals to K. So if I want to consider many, I will say N1 V1 equals to N2 V2. So this is number of molecules. Then this is the volume. Okay. So you see, very easy. Just know that what is constant is temperature and pressure. Then number of molecules is directly proportional to volume. That is what Avogadro's law is saying. Okay, that's what it's saying. Alright, so that answers that. So I think what other things have we not talked about? The other things I listed then. Where is it? Okay. Now we talk about this. 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 Now ideal gas. This is very interesting because of these conditions. Now, ideal gas is a very interesting thing, right? Because just like I told you, there's nothing like ideal gas. We just use an assumption. But there's a particular curve you must understand is when you have pressure and volume. We already established the fact that as this guy increases, this will come here, this will go like this, this will go like this. So if you have this, this is pressure volume, that graph we did that time. So this is normal because this what's it called, this Boyle's law that we stated then is still following the concept of ideal gas. So that's why this one is ideal. But in the context of a real gas, look at it. So that means this curve, this is Boyle's law curve, right? Now that means this curve is following what? Ideal gas. This is the curve of ideal gas, right? Now, if in the context, it means that if I'm talking about real gases, those one will at a pressure, they will have an increase in volume. So that's why this one will now shift forward. This is the same pressure here. There's a, let me say I'm starting from 1, 2, 3. So the pressure here is 2, right? So this at pressure of 2, it will not be this volume that it is going to use for real gases. So it will shift it to the front, such that the curve will now go like this. So this is the curve of a real gas. So never forget. Never forget. Never forget. So what is just important is that what I want you to know that at this same pressure, the volume that a real gas we need is higher than this is for ideal gas. That's what, and this is for real gas. That this is for real gas. So take note of that. Take note of that, please. I would have taught you other things, but that would be for that post you hear me. I would have taught you compressibility factor. When you are comparing, different gases. What about if it is straight? No, good. I like that question. If it is a straight curve, like we already established the fact that it can be P all over 1 over V, right? Now, if it is a straight line like this, what's just important is that we already established that P is directly proportional to this. This curve you are seeing here is for ideal, right? That means you will just have an increase to this, but it will not be this manner. You understand? So just this is what this curve is important, because this is a curve you must know. So please take note of that. This is real gas. This is the curve for ideal gas. Now let's move a bit ahead. Now please note something. That means there are conditions for gases. There are conditions. This one is a JAMB question. For gases to deviate from ideal behavior, right? There are conditions for gases to deviate from ideal behavior. Then how do I know those conditions? Because I don't want to disturb myself. I just said most of you have HP laptop, Abby. Most of you have HP laptop. So that is the answer to that question. What does HP laptop mean? It means high pressure. These are conditions for gases to deviate from ideal, for them to be behaving like this, right? High pressure, L is what? Low, then T is what? Temperature. So at these conditions, gases tend to deviate from ideal behavior. So your HP laptop is the mnemonics. HP laptop, low temperature, high pressure, so they deviate from ideal behavior. That means, let me ask you a question. Code Rise, what do you think the conditions for ideal gas will be? Who can tell me? If you follow what I just said, this is the only thing you need to know to even know this one. So what is the condition for it? If gases are deviating at high pressure, low temperature, what do you think the condition for ideal gas will be? It will just be the opposite of this. It is the opposite. Number one is what? Low pressure. So a gas at low pressure. And number two, high temperature will behave like an ideal gas. Thank you, Jerry. Debbie, God bless you. Exactly. It will just be the opposite. You see that it's easy. So just know this one for deviation. Then you just reverse it for the ideal gas. Okay? So that is it. It's not hard. These stuff are not hard. Okay? Are we good? Good. So now let's talk about the last thing, which is the ideal gas equation. Do you get it? Do you get it? Do you get it? Do you get it? If you want to snap now, or you can also rewash. I'll put it live. Good. Now let's ideal gas equation. This is very, very important. Right? Now what actually happens in ideal gas equation is just having PV equals to nRT. But this is not to cajole you or anything. But what it's actually talking about here is just saying that PV is directly proportional to NT. So the same way we have been doing PV, if I'm introducing an equal to sign, this thing must introduce a constant. The constant here is now R, then NT. So if I need only R, that's why it is PV divided by NT, because that's what is attached. Then RNT divided by NT. This will go with this. Then I have PV over NT equals to R. Now, this is very important because this R is what they call what? Ideal gas constant. Ideal gas constant. Okay? Now, it has a unit, it has a value. How do we get it? Now, don't forget that this is actually pressure, and this is what? This is volume. All over, this is what? This is mole, N is mole, and this is temperature. So that is what is just having here. That is what is equals to the R, which is the ideal gas constant. Anyways, what is just important is that there are values for these things. But what I want you to note is this pressure can be the SI unit of pressure. Who can tell me what is the SI unit of pressure? Do you know that there are a lot of units of pressure? Do you know that? I'm very sure you know that. The number one, we can talk about what unit of pressure can be in Pascal. Unit of pressure can be in what? Atmosphere. Unit of pressure can be in what? I'm listening now. Can be what? Millimeter per mercury. The SI unit of pressure is Pascal. Good. Unit of pressure can be in millimeter per mercury. It can be in bar. In fact, it can be in PSI. PSI, but don't worry, this is not for a level. PSI. This is pounds per SI, like SI. But don't worry, it can be in PSI. But I'm very sure you guys are familiar with this, right? And you note that who can tell me 760 millimeter of mercury in atmosphere? Well, this you know this, but let me just ask. 760 millimeter of mercury, it is what? 1 atm, abi? But that is not where I'm even going. What I just want you to know that, just take note of that. So that means if the unit of pressure here, for instance, is Pascal, volume here must be what? Let's say it's meter cube, the SI. Then this one is mole, which is the unit, and temperature is in Kelvin. That means I can get the unit of this guy, because I know that pressure times volume is actually work done. Who knows that pressure times volume is work done? Hope you know that pressure times volume is work done. Or should I prove it for you? Let me tell you how that is so. That means, let me tell you how that is so. Look at it. Pressure times volume is actually work done. Work done times volume is work done. You will see now. Pressure is proof good. Pressure means force over area, times volume means area times height, right? So if area cancel area, it's like I'm having force times height, and height is a form of distance. So force times distance equals to work done. So that is why pressure times volume is work done, because that's what gives the unit. So from there I can say that, I want to derive R, so I can say from here that pressure times volume over mole times Kelvin. So because I already know that this guy is work done over mole times Kelvin, so that's why the unit of R, work done, the unit of work done is what? Is joules per mole, per Kelvin, sorry. It can be anywhere anyways, then per mole. So that's the unit of R. Or I can say that R is, you've not seen it, per Kelvin per mole. Now don't forget, because I'm using joule, this thing has a unit. So the unit will be what? 8.31. This is many units. It has a value, sorry, not saying that, I didn't mean units. But don't forget, is when I'm using joule per Kelvin per mole. Now I don't dispute the fact of what you see in your other textbook, that you say something like 0.0083. Let me see if I'm correct. So 1, 2, 3. Yes. So but that one we have kilojoules, right, per Kelvin per mole. Send me a message. This is my number. Screenshot right now to join the WhatsApp class. 24 71 75. This is my WhatsApp class. My WhatsApp number. Send me a message on WhatsApp to join. So can you see? Now how do I know that this is correct? Because I know that 1 kilo is 1,000. So by the time I replace this with 1,000, it will just take this guy from this 1, 2, 3 to 3.31 joule per kilo per Kelvin. Why am I saying kilo? Per Kelvin per mole. So this is what they call ideal gas constant. So it's easy. All these stuffs are easy. Chemistry is easy. So are you good to go? Do you get that? So if you want to join the WhatsApp class, you can send me a DM here. You will learn a lot. So hope you guys get something. Hope you guys have been able to dismantle, the concept of gas laws, in this video. I've been able to dismantle the concept of gas laws in these videos. Okay, let me just, I didn't write the graphs for Charles' law and the like, so that you can get that. So when I make graphs for Charles' law, for instance, we already said Charles' law is volume directly proportional to temperature. So I can have V here and I can have T here. So when I have volume in this, such that this is, let's say, Kelvin, for instance, so it's just directly proportional, so that's why it will be a straight line. But don't forget, I can also have volume so that this T is in degrees Celsius, and I have a particular volume here which is called -273 degrees Celsius. So this guy, or if you don't call it -273 degrees, it's called 0 Kelvin. So this is called absolute zero temperature, right? So these are the two graphs for Charles law. So please take note. So this is number one. So from the motion of gases tend to cease, right? So in this case, you can now go like this. So that's why you will see another graph like this. But don't ever forget that there's a value here, which is either 0 Kelvin or minus 273 degrees Celsius. This is another question. This is called absolute zero. So if it is pressure law graph, very easy. Just like the name, the way you see it, pressure is directly proportional to temperature. So when you have V and T directly proportional, just pick up from here and go like this. So I hope you've gained one or two things. If you want to register for the JAMB classes, you can send me a WhatsApp message here. You can send me a WhatsApp message here to register. So I will see you in class. Again, make sure you subscribe if you have not subscribed. I post video here every day. The chemistry tutor is the name. So bye for now. I hope you gain one or two things, okay? Yeah, bye bye. I'm going to TikTok now. The name is still the same thing. I want to go and teach on TikTok small. So anyways, you can see me on TikTok. Go subscribe to my TikTok. It's also the same way on IG, Facebook, anywhere. It's still the same name. So bye. I will see you when I see you.